going to have some M0 nodes to begin with. Okay, so M0 is like the initial number of nodes that are out there in the network. And then what happens is you set up some links between among those M0 nodes such that each node has at least one edge incident on it. Okay, then new nodes join the network. Okay, one at a time. So we look at each node joining at a particular instant. Okay, so M0 is 2 in this case because you have 2 nodes initially, and you have an edge between them. Now, after that, the joining process starts. So the new node comes. So we indicate the new node with the white circle and the earlier node already there with the black circle. So the new node comes as one node, and each new node gets some links to the existing nodes. So we say m new links are added with each join. So with each joining event, m new links are added. So the new node is attached to m existing nodes. Okay. So m is also 2 here, so the new node gets the edge to each of the existing nodes. So in the next time instead, these 3 nodes become old nodes, so another new node comes. So you have like the new node that comes can attach only to 2 of the existing nodes. So we'll see there's a probability with which the existing nodes will get the new link with the newly joining node. Okay. So we'll see what the probability is soon. So this new node is attached to these 2 nodes. Okay, so it's not attached to this node. So now the next time instant, these 4 become old nodes or existing nodes, and this is a new node that joins. So as you can see here, this particular node has a larger degree. It has degree of 3. Whereas and this one also has a larger degree of 3, and these 2 nodes have degree 2. So this new node gets its 2 edges, one edge to the node with degree 3 and the other edge to a node with degree 2. Okay. Now let's see one more. So this is these are the existing nodes. A new node comes, and it gets 2 edges with this node that has like already degree 4, and this node has a degree 3, and keeps going on. Now this node comes in, it also attaches to a node with degree 5 and degree 3. So what you can observe, the new node comes here, joins with a node with higher degrees. So as the new node comes, it prefers to attach itself to nodes that already have a larger degree. Okay? So this is the nature of this model. So when a new node comes, you need to decide among these 1, 2, 3, say 8 nodes, which 2 nodes get the new link. Okay? So you decide the probability. But the probability is modeled in such a way that priority is given to nodes that have a larger degree. Okay? So what is that probability function that decides which node gets a link? So this is the probability function, and we'll do a lot of problems after this based on this. Okay? So we'll first try to understand the notation. Let ki, so the new node, each node joins a time instance at ti. So let ti indicate the time at which node I joins the network. Okay? So ti is a time at which node I joins the network. Okay? So ki is basically, so we can indicate like this. It's a function of t. As you can see, the degree of the nodes change with time, isn't it? So this node had degree 4, but after a while the degree might have become 6. So the degree of a node node changes with time. As new nodes come in, and if they get attached to the existing nodes, the degree of the existing nodes increases, right? So we denote something like Ki of t is basically the degree of node, basically I, that join the network at time ti. So the degree of node I, so if I say degree of node I, it automatically implies that node joined the network at time ti. But this is the degree at some time t. At some time t greater than or equal to ti. So the node joined at some time ti, and its degree keeps on increasing. So Ki of t is the time at which you are measuring the degree of the node. So this time could be greater than or equal to the joining time. Okay, so I join the network at time 10, and what is the degree of that node at time 100? We can indicate it like this: K10 of 100. So that means the degree of the node that joined the network at time 10 units. What is the degree currently at time 100? Is that clear, the notation? Okay, so Ki of t means the node joined at some time ti. So that also is the ID of the node. So the joining time ti is the ID of the node I. And what is its current degree at some time t greater than or equal to ti? Okay. So the probability function is, so you have some nodes that are already out there. Okay. So you associate, so each node has like Ki is the degree of node I, right? So the probability for this node Ki, for this node I with the degree Ki to get the new link is going to be Ki divided by sum of all the nodes that are out there, sum of the degrees of the nodes that are out there. Okay, so that is given by the probability for node I to get the new link. So the probability for node I to get the new link is going to be its own degree divided by the sum of all the degrees. So you could think about like this, and we'll see some math problems in detail later. So if, say, the network was something like this. So this node has degree 2, this node has degree 3, this node has degree 4, this has degree 2, this has degree 3. Okay? So the probability for this node is going to be what? 4 divided by the sum of all the degrees. So 2 plus 3, 5 plus 8 plus 10, 14. So this is the probability for this node to get the new link. Whereas this node will have a probability of 2 over 14. Is that clear? So which means a node having a higher degree is more likely to get the new link. Okay? So how we simulate it, we'll see in the examples. Okay? So right now we have to just know that nodes that have a larger degree will get more links basically. So so scale-free networks, I think I might have mentioned earlier, this follows what? The rich gets richer model. There is like this saying, isn't it? So which means the nodes that already have a larger degree tend to get more edges, incoming edges. Okay? So in that sense, nodes that joined the network earlier would likely grow larger in terms of degree, right? So if you look at the degree distribution, the growth rate, okay, we'll see the finer details of this distribution as we proceed, but at least for now we should understand this. So this is the growth of the degree of the nodes with time. Okay, so we'll call the network evolution. Evolution means as the network grows with time. Okay. So the 10 indicates the joining time of a node. So some node joined at time 10. So at time 10 its degree started growing like this. Okay? Some node joins the network at say time 300. So the last black line. So its degree started growing like this. So these are the joining times of the nodes. So starting from those time instants, how their degree grows with time. So as you can see, the node that joined the network at time 10, so every new node at the joining time gets that m links. So the newly joining node gets only the same degree at the time of joining. But after that, the degree grows, right, at different rates. So the nodes that joined the network earlier get even more bigger, larger degrees, so they grow at a very fast rate. Okay? Whereas the nodes that joined later, okay, their degree grows at a very slow rate. Is that clear? Because why is that? With time, as time progresses, more nodes join the network, so there's a lot of competition, isn't it? Because each new node gets only the same number of links, m links, for every joining instant. So if you had say 5 nodes, this node had a probability of 4 over 14. But if you had say 10 nodes out there, this particular node, its degree is currently 4, it might have increased to 6. But you know the other nodes also have degree. So it might be like 6 over 30. 6 is its own degree plus divided by sum of all the degrees, so that is 30. So even though the degree of this node might have increased, when you compute the probability, it will be lower than what it was at the earlier time instant. Is that clear? So as new nodes join in, the total number of nodes in the network increases, so the chances of a particular node to get the new link will decrease. There are only 4 people and I come in and I want to attach to 2 of you, there are more good chances that one of the 4 will get a new link, right? But if there are 10 people and I come and I want to still attach only 2 people, then the chance that an individual person will get the new link will be less. Makes sense, right? And especially the nodes that joined later, because the whole probability is based on degree. As the degree grows at a slower rate, the nodes that joined in the later time instant will have a less chance of getting the new link with an incoming node. Okay, so that's the nature of this Barabasi-Albert model. So that means what will happen eventually, why this it has been designed like this. You want to build some hub nodes, because scale-free networks have some hub nodes, right, that have a larger degree, but they're few in number, but they're still in appreciable number, and most of the nodes have lower degree. So most of the nodes means like that have lower degree or those nodes that joined in all these later time instance. So the nodes that join the network at the earlier time instance end up being the hub nodes that have a larger degree. Okay, and the scale-free distribution, the power law distribution can be observed. So if you plot, okay, so we want the K, this is PK model, to look like a power law distribution like this. Okay, so let us get into the details now. So this Ki of t, okay, so again, as I said, this is the degree of node I that joins the network at some Ti, and we are measuring its degree at some future time t greater than or equal to Ti. So there's a derivation of this for this expression according to this model in the Barabasi book, okay, but I'm just giving the final expression. So Ki of t is computed like this, okay, m times t over Ti raised to beta. Now I said what m is. M is the number of new links that each node gets at the time of its joining. Okay. T is the time at which you're measuring the degree, and Ti is the joining time of node I. Okay. Now this beta is called the network's dynamic exponent, and it is a constant. Okay. So it is typically half. Okay. According to this, for this model, it is a constant. Okay. So we are looking at something called Barabasi-Albert model after the name of the 2 people who came up with this. Okay, so BA model. this is the formula expression for the degree of a node at any time. Okay. Now, let us do this differentiation. You all know how to differentiate an expression, a function. So if I have ki, so the variable here is t. Everything else is a constant. Ti is a constant, beta is a constant, m is a constant, everything else is a constant. So if you differentiate this function of t with respect to t, it's going to come out like what? M is a constant, so it's going to be beta times, again, ti is a constant, so I can take this outside. So this is going to be t raised to beta minus 1. Right? So if y equals, say, x to the power some constant b, if you differentiate with respect to x, what's the formula? B raised to b minus 1. Right? So let me simplify this a little bit here. So other than t, everything is a constant. So all these things are constant. So this is the only, t is the only variable. Okay? So if you differentiate this, the constant stays as it is. So according to this, the beta comes first and then t raised to beta minus 1. Okay? Now, as I said, beta is typically half. So let us substitute that half. So this is m divided by ti to the power of half. Beta is half. T raised to half minus 1. So half minus 1 is negative half. Right? So if you simplify this further, what's going to happen? It's going to be like m divided by 2 ti to the power of half. This is t to the power of negative half. So what is t to the power of negative half? I can write it in the bottom and say it is t to the power 1 over t to the power of half. Right? So what is something to the power of half? Is actually square root. Right? So I can write it as m divided by 2 square root of t times ti. So that is your differentiation. Okay? So let us see if it is the same thing here. Yes. So if I differentiate ki of t, this is what you end up with. Okay? So we can also get some important information from this expression. So what does dki over dt indicates? This is a rate of growth or rate of change in the degree of node that joined at time ti. So what is its change? The degree with time, okay, as time increases. And what is here? Again, t is a variable, the other two are constant, but still what you can see, if this ti is in the denominator, right? So, which means if a node joins the network earlier, its degree will change faster. And this is all positive slope, like positive increase. So, its degree is going to increase faster compared to a node that joined the network later. So, if everything else is fixed, okay, it means you have, say, two nodes, like I showed in the figure before. So if you have two nodes A and B that join the network at time TA and TB, TA is going to grow faster with time. So we're measuring at some time T. But TB is going to go slower with time. So the rate of increase, right? As you can see in this figure. So this is a faster increase with time, whereas this is like almost a horizontal line. It doesn't increase much with time. Is that clear? So the slope here is larger, the rate of increase is larger, whereas here the rate of increase is small because of the Ti in the denominator. So the node that joins earlier will get a faster increase. And not only that, again, since the Ti is in the denominator, right? For any node, you see here the increase here for this node is like very steep compared to maybe this is not a good one. Of course, I drew it manually, but you see this one, this is a more steeper increase, but as time progresses, it kind of slows down. Now it's very late. Keep it separate. It's very late. Is that yours or somebody else?
It's Raj.
Okay, keep that separately too. Okay. So the rate of increase here, this is T. Okay, whereas here it slows down. Okay. Similarly, it's increasing faster here for every node, for any particular node, whereas it becomes very horizontal. Okay, again that is because the Ti is in the denominator, right? So as the time grows, and the T is also in the denominator. Look at this. So T is in the denominator. So which means as time increases, the rate of growth decreases with time. Okay, so because both Ti and T are in the denominator, for any node, as time increases, its rate of growth decreases in the degree. And also between any two nodes, since Ti is in the denominator, nodes that join the network earlier will get a larger increase. Okay, and nodes that join the network later will get a slower increase. And for a particular node, with respect to this T, since it's again the denominator, as time progresses, so as time T increases, the rate of increase will slow down. Okay, so have you seen in any math class so far this concave up, concave down, and all this stuff? No? Yes. So they would have taught differentiation stuff. So we can kind of assign a kind of a pattern. Okay. So let us just quickly see these terminologies. So we say something is concave up if the rate of increase or decrease. So the function could increase or decrease with time. As increases with time. So the rate of increase or decrease should increase with time. So it means like, so this is a function. So if you measure the slope at an earlier time and if you measure the slope at a later time, the slope here is smaller than the slope here, right? So it increases faster with time. Similarly here, the slope here is going to be what? So it decreases, and as time progresses, the decrease is still appreciable. Okay, whereas here it increases, but the rate of increase here is going to be larger, whereas the rate of increase here is going to be smaller. It kind of becomes more or less horizontal, right? So such functions are said to be concave down. Similarly here, it decreases. The decrease here is much steeper, whereas the decrease here is not that much. So we say this is again concave down but decreasing. Okay. So our degree function increases like what? It increases like this. It's faster in the earlier stages, but as time increases, it increases slowly. Okay, so that is why we say our degree function was concave down increasing. Okay, so that's why I say here it's concave down increasing. So that's the way in which the degree centrality of the nodes increases with time. Okay, so every node, the degree increases as new nodes join, but it increases at this rate, okay? The pattern of increase. Now, just for curiosity, if you are interested in the change in the other centrality metrics, so we can call this as time-dependent variation. So, how the centrality metrics change with time as the network grows with time. So, if you evaluate the betweenness centrality of the vertices of the nodes in the network, it will show this pattern. So, this pattern is concave up increasing. So, it's again increasing function. It's not like slowing down with time, it's actually increasing with time. So the betweenness of the nodes, especially the nodes that joined earlier, okay, the betweenness of those nodes will increase much faster as time progresses. So as you can see here, this node, its betweenness was increasing at a certain rate. But as time increases, the rate of its increase will shoot up, will increase with time. Okay? So, if you read this paper, you can also look at the rate of increase of the other centrality metrics, or increase or decrease, like eigenvector centrality, closeness, and so on. Okay? Any questions so far? Okay, so this was the Barabasi-Albright model. Let me make sure if I missed something. So, what is the weakness of this model? If you want to use this to simulate the evolution of real-world networks, okay, it could result in the scale-free degree distribution and so on, the power law distribution and so on. But there is one problem. What is the problem? It gives preference to nodes that join the network earlier. So, as I showed, if you have 3 different nodes that join the network at 3 different times, the node that joined earlier, the red node, its degree just keeps on increasing at a faster rate compared to the green and the blue ones that joined later. So think about it like this, in a social media, right? So in social, Facebook and all this social media, you have a celebrity who just comes and joins the network today, okay? So like take the case of Twitter, isn't it? So already there are a lot of people in Twitter and they have some followers. But a celebrity who is well known in the industry and so on does not have a Twitter account so far, but just comes and opens a Twitter account. Within a day or two, the number of followers for that celebrity would have just increased because that person is known in the industry and many people will just come and follow, right? So if you try to kind of model or generate a Twitter-like network using this BA model, not work, because if the person joins the network later, their degree should not grow faster than the degree of the people who are already out there, right? But Twitter kind of networks, most of social networks will exhibit this pattern, right? So if this blue node joins the network later, but it has some metric associated with that user, like popularity or whatever, that will make the degree to just shoot up, right? Because as more followers join, the degree will just increase, should increase, right? And eventually, their degree, or like the number of followers, should even go beyond the number of followers or the degree of the nodes that joined the network earlier. So as you can see in this figure, the red one joins the network earlier, so its degree kind of keeps increasing. The blue one joined later, but say the popularity of that node is much larger, so its degree just keeps on increasing at a faster rate. And eventually at this time instant, the degree of the blue node goes beyond or is larger than the degree of the red node. Is that clear? And there is another node, say the green node, that does not have much popularity, so even though it might have joined earlier, its degree grows at a very slower rate. Okay, so the joining time is not the only deciding issue. Here, joining time is the only thing that decides how the increase in the degree is, right? So we want some model that takes the joining time into account, but also something outside, other than the joining time, something external, something that is unique about the node. okay, like the popularity or depends on the network, okay. So we'll call that as the fitness. So each node will be associated with a fitness parameter, okay. So the nodes that have a larger fitness, even though they may join the network later, their degree will eventually grow faster, okay, and become larger than the degree of the nodes that joined earlier. So we denote that with this eta symbol, okay. So here, if you cannot see this, so the blue node has an eta of 0.991. It could be even larger than 1, okay. And the red one has 0.223, and the green one has 0.185. So the blue node that joined, that was the latest to join, okay, since it had a larger fitness value, its degree eventually will shoot up and go beyond the degree of the other two nodes. Okay, so this will be able to model a real world network more closely, right, compared to this model. So this is called the Barabasi-Bianconi. Okay, so I need the students of Barabasi, I guess. So the BB model. Okay, so the BB model is kind of more close to reality compared to the BA model. Okay, it's built on top of the BA model, and it takes into account the fitness or something that kind of is unique up for each node. Okay, so the degree function, like we had Ki of t here, this is the Ki of t according to the BA model. So this is the Ki function with respect to the BB model. Okay, so here this fitness has to be taken into consideration. So the degree of a node that joins the network at some time ti, and you are measuring its degree at some future time t, and that node I has a fitness indicated by eta I. So everything is based on the joining time, symbol notation. So eta I is the fitness of the node that joined at some time ti, okay, and you are measuring its degree at some future time t. And that's calculated like very similar to this, m times TOTI. The difference is in the exponent. So I said in the BA model, the exponent is a constant, it is half. Whereas in the BB model, the exponent is a function of the fitness. So we say beta of eta I, means the exponent that the value of the exponent used here is not always half. It depends on the fitness of the node. If the node has a larger fitness, it probably has a larger beta value. Okay, otherwise it depends on the eta. Okay, so because it's an exponent, so if nodes have larger fitness, what happens? The degree will just increase like this, explode with time. If the nodes have a smaller fitness and beta is a function of eta I, what will happen? The degree will not increase that faster. Okay, so that's why we have the beta, the exponent, as a function of beta I. So larger fitness, more faster increase with time. So clear? So that is how we have to interpret this expression. So if you differentiate this and rearrange the terms, this is the probability. Okay, so in the BA model, I said this is the probability with which you decide whether a node gets a new link or not. And that probability is just based on the degree of the node at that time, Ki. Whereas the probability with which a node gets a new link according to the BB model is basically this. Okay, so actually this is not the probability expression. So this is the probability expression. This is the rate of growth. Okay, so I'll write the corresponding probability here. So this is the BA model. So in the BB model, the probability is going to be a function of both Ki as well as eta I. So it is eta I times Ki divided by summation of eta j kj for all nodes out there. So which means each of these nodes has some degree as well as a fitness. So you multiply the degree and fitness. So it's a degree fitness product divided by the sum of the degree fitness product for all the nodes out there. So nodes that have a larger degree as well as a larger fitness are more likely to get the new link compared to nodes that have a smaller fitness or a smaller degree. Okay, and this expression dk over d, right? So this was for the BA model, whereas this is for the BB model. Is that clear? Okay. Any question? Okay, so let us do some math problems. So it will be reinforcing what we just saw in theory. Okay. All right. So let us say you are given the nodes that are currently out there. So currently you have say 7 nodes in the network, and this is the degree of those nodes, and this is the fitness of those nodes. So a new node, say the 8th node, joins the network, and the new node is supposed to get 2 links. So we want to decide which of the 2 nodes among the 7 nodes will get the new link. So each node will get only 1 link. Okay. So we have to pick 2 of the 7 nodes out here to get the 2 new links. Okay. According to each of the models, according to the BA model and according to the BB model. So let's first do the BA model. So the probability formula for the BA model is this. So it is the Ki divided by the sum of all the degrees. So let us omit the fitness column for now for the BA model and just work based on the degree values. So what is in this expression here? We want to first sum all the degree values. So we'll sum all the degree values, and that comes out to be 20 here. So we divide now the Ki, the individual degree values, by the sum. So that's the probability, okay, for a node to get the new link, which is the first link. We want to add 2 links also, remember that. Okay, for the first link, what's the probability for each of the nodes to get that first link? So we divide its degree by sum of the degrees. So 1 divided by 20 is 0.05. Then 4 divided by 20 is 0.2. 5 divided by 20 is 0.25. 3 divided by 20 is 0.15, and so on. So just the individual degree divided by the sum. Now what we do? We find, of course, the sum of all these individual probabilities should be 1. Okay. Now we'll go ahead and find what's called the cumulative probability. You all know what a cumulative probability means. So this is the individual probability. So now for node 1, the cumulative probability is also 0.05. For node 2, it means you're considering both 1 and 2. So you have to add up 0.05 plus 0.20, so that's 0.25. So for including node 3, the cumulative is 0.25 so far plus 0.25 for just node 3, so that is 0.50. So the individual probability indicates the probability that node 3 will get the new link is 0.25. The probability that node 4 will get the new link is 0.15. What the cumulative probability indicates? The probability that nodes 1 or 2 or 3 will get the new link is going to be 0.5. The probability that nodes 1 or 2 or 3 or 4 or 5, so up to node 5, any one node up to either 1, 2, 3, 4 or 5, one among these 5 nodes will get the new link is 0.80. Which means if you keep on adding like that, the last value should be 1, isn't it? So that means the probability that one among the 7 nodes will get the new link should be 1, right? So again, how to get the cumulative probability? The first node is the same. Then add up like this. So 0.05 plus 0.20 will be 0.25. Then add these 2 should get this, then add these two should get this, then add this with this should get this, and so on. Okay? So 0.80 plus 0.10 should be 0.90. Then 0.90 plus 0.10 should be 1. So finally you should end up with 1, otherwise you have done some mistake in the calculation. Is that clear? So why we calculate the cumulative probability? Because again our ultimate goal is to pick one among the 7 nodes, right? So after we find the cumulative probability, we generate a random number between 0 and 1. Okay? So you know how to do that. Just use an Excel spreadsheet and just pick a random, generate a random number. And let us say the random number that I get is say 0.2429. So then what you should do is you should pick that node that is closest to it but still larger than this. So this value 0.25 is the closest to 0.2429 and still greater than or equal to that value 0.2429. So the corresponding node 2 will get that new link. Okay? So why is that again? So think about like this. So another way to visualize.
Sir, how we get 0.2429?
That's like a random number. So you know the other day I showed just use the rand function in open Excel sheet and type rand equals rand in Excel to give you a random number, or use a calculator to generate a random number. Okay. So if you draw the scale from 0 to 1, okay, this 0.05 for node 1 is the range from 0 to 0.05. Then this is 0.20, so that's for node 2. Okay. Then 0.25 for node 3. Then 0.15 for node 4. Then 0.10 for node 6. Then another 0.10 for node 7. This is like the distribution. So as you can see here, if I generate a random number, it could be anywhere from 0 to 1, right? So the chances for the random number to fall within a particular bin, so each is like a bin, right? So the chances for the random number to fall within a particular bin is going to be high if the bin width is larger, right? So if the bin width is smaller, like this, so this is the smallest width, the chances of the random number, it could be any value, that's why it's called a random number, right? It could be any value from 0 to 1. But the chances of it to be within this range is going to be smaller, within that bin. Whereas the chances for the random number to fall within this range is going to be larger. Okay? So that is why you find the cumulative probability, because the random number could be anywhere from 0 to 1. So the chances that the random number would be, like the sum of these two is what? 0.25 and this is what? 0.50. Right? So that is this range.
Oh yeah, 50. Yeah.
Is that clear? So the chances for the random number that you generate to fall within this range is going to be larger compared to the random number falling between 0 to 0.05 or down here 0.80 to 0.90, because the width here is just 0.1 whereas the width here is 0.25. So chances of the random number to fall within this bin is going to be larger. Of course, that's not the only thing, it's still a random number. As we see in this example, we got something that falls within this range. So 0.2429 fell within this range. So node 2 got that new link. So it's not guaranteed, it's only a probability that if you have a larger probability, you are more likely to get the new link, but not guaranteed. Is that clear? So that is how you have to interpret this. So it's like a simulation process. Okay? So now that you know that each node has only a probability to get the new link, how to really decide which node gets the new link. Okay? So this is how we do it. Is that clear? Okay?
So in order to get new link, we calculate cumulative probability?
Yes. Calculate the cumulative probability. So that is that basically gives you a distribution like this. So now generate a random number and see within what bin it falls under. Okay, so it falls within this range of 0.05 to 0.25. So node 2 gets that new link. Suppose if my random number is like 0.04, which node gets the new link?
3.
My random number.
Oh, just a random number.
1.
Node 1, the first node, because it is less than
Oh, yeah.
0.05. So anything less than or equal to, actually it's less than. So anything less than 0.05 should belong to node 1. Anything 0.05 to anything less than 0.25 should be node 2. Okay, because we are assuming the random number is going to be, it could take the value 0 but cannot take the value 1. So the largest random number you can generate is around like this, 0.9999. It cannot be 1. Is that clear?
Yes.
So the last if you generate something like 0.999, it will fall within this last bit. Okay, is that clear? So now that we have decided which node gets the first link, we can use a similar process to decide which node gets the second link. So what you do for that? Now that we decided node 2 gets the first link, we repeat the same calculations, but by omitting the second node, because it has already got the new link, right? So it cannot get the second link also. So what we'll do now, we will discard node 2 from our calculation. So this was a given original list.
We will start from the beginning.
So we'll start from the beginning, but without considering node 2. So as I show here, we consider only nodes 1, 3, 4, 5, 6, and 7. So we repeat the same process without considering node 2. So we'll do the same. So sum all the degrees, which is 16 now, and divide the individual sum by the degree. So 1 divided by 16 is 0.06. 5 divided by 16 is 0.31, and so on. So now again find the cumulative probability. So how to find the cumulative probability? 0.06 for the first node, the same. Second node, 0.06 plus 0.31. I did this in Excel, so there's some round off thing. So this is 0.38, then 0.38 plus 0.19 is 0.56, and this plus 0.19 is 0.75, and so on. Okay. So now I generate a random number. I get the random number to be a very small value, 0.0022. That falls under the first bin. So the new link should go to node 1. Okay. So if I generate again another random number, I may not get the same random number. So it depends on the random number that you generate. Okay, but still, again, as I said, it's probability. So if I give this problem to each of you, as I said before, each one should get a different random number, and each one should get a different new link, a different node to choose from, right? So don't make the mistake of copying and just write the same answer.
Like each random number is different, so our nodes will be different.
Your nodes should be different. Okay? Any question?
So you keep going through this process until you no longer have any nodes?
No, you decide that number of new links. So that M is a parameter that is decided ahead of time. So each new node gets only 2 links. So this is how you decide which of the 2 existing nodes get the new links. So in this example, nodes 1 and 2 get the 2 new links. So after that, node 8 will join the network. So node 8 has joined the network now with its degree being 2, right? Because it has got the edge to node 1 and 2, right? So, and it will have some fitness.
Oh.
So this is now the updated status. So now node 9 tries to join the network.
Okay.
So now you repeat the process of finding which 2 of the 8 nodes will now get the new link with node 9. So after that, node 9 will join the network with this. Of course, as node 9 joins, the degree of these nodes will change, right? So already node 1, its degree will be 2, and node 2, the degree will be 5, because node 8 is now attached to these 2 nodes, right? Now as node 9 joins, then the degree of some other node or even these 2 nodes will increase. And then node 10 will then join the network.
So this goes on.
That's the
goes on
evolution
for-
of the
yeah.
network with time.
Okay.
So that is how you are able to get this degree distributions like this. So all these indicate the nodes join at subsequent time instance, and the degrees of the existing nodes increase
Yeah.
with time as new nodes join. Okay. So we can repeat the calculations for the BB model. So the only difference is you have to now consider the fitness. Okay. So what you have to do is find the degree fitness product. Okay. So for the BB model, you have to consider the fitness also. So find the product of the degree and fitness. So 1 times 5 is 5, 4 times 4 is 16, 5 times 7 is 35, 3 times 10 is 30. So then once you multiply them, add them up. So why we have to do this? Because we have used this formula. What is that? Sigma, Ki, eta I divided by the summation of all the Kj and eta j. So now what you do to find the probability? Divide the individual product value 5 divided by the sum of all the product values. So 5 divided by 140 is going to be 0.04. Then 16 divided by 140 is 0.11. Then 35 divided by 140 is 0.25 and so on. So these are now your probability values. Then as usual, find the cumulative probability. Okay? And so cumulative probability is same as the first node, and then 0.04 plus 0.11, 0.15 and so on. So once you get the cumulative probability, generate a random number. So it comes out to be 2.2584. So look into this. So which node should get that new link if the random number is 0.2584? The closest and largest value is 0.40, right? So node 3 should get that new link, first link. Is that clear? Okay? So that's the first link. Now for second link, what you should do, discard node 3 from your calculations and repeat the process. So remove node 3 and just repeat the process. So find the degree fitness product. So the sum of the product values is 105 and divide the individual product values by the sum of the product values. So sum of the product is 105. So the individual degree fitness product divided by the sum. 5 divided by 105 is 0.05. 16 divided by 105 is 0.15 and so on. So once you get the probability, find the cumulative probability again. It comes out the random number, let us say 0.4885. So what's the closest and largest value?
4.
0.49, right?
Node 4.
Node 4. So node 4 should get the second link. So under the BB model, nodes 3 and 4 got the two links for node 8. So node 8 tries to join the network, and which two nodes among the 7 nodes are chosen for the new link? According to the BB model, it is 3 and 4. Now if you look at the numbers here, nodes 3 and 4 have reasonably larger fitness compared to the other nodes, and that has a say in those two nodes being chosen. Of course, you have also some larger fitness values, but they have a larger fitness as well as a kind of larger degree. So the combination of degree and fitness. So if you have a larger degree and you have also a larger fitness, so you have more followers and you are known well. So the fitness is a measure of how something that you characterizes that node. Okay, so like if you are known to everyone out there, that's a measure of fitness. If you are not known to everyone out there, then you have lower fitness. Okay, so this is according to the BB model. So try to come up with numbers like this on your own. You can also try.
So the only difference is like BA and BA model is like here is multiplication of degree and fitness.
Right. And that plays a role. You see, degree is something network dependent metric because it changes as the network grows and so on. And remember that the fitness doesn't change. Once a node joins, its fitness remains the same. Okay, so node 1 joins the network at time 1. Its fitness is 5, and its fitness remains throughout the evolution process as all the new nodes join. Because degree may change, but the fitness will not change. Okay, so fitness is not time varying thing. It's just a fixed value, but different for each node. Okay, so each node may have different fitness. Okay, so fitness is an offline parameter, whereas degree is an online. It depends on the network and how it grows with time. So the combination of the two is used to design the new link under the VB model. Okay? Alright, so we'll do some more problems later on this and then we'll